Hello, my name is Jonathan Coria, and I'm a biochemistry student at the University of Texas at Arlington. I'm currently conducting research under the guidance of Dr. Peter Kroll, a physical chemistry professor whose research focuses on polycrystalline ceramics through computational chemistry. The research that I'm performing focuses on the diffusion of nitrogen in amorphous silicon nitride across a range of different temperatures for certain periods of time through the use of molecular dynamic simulations. Silicon nitride ceramics are polycrystalline structures that are known for their thermal stability and shock resistance at high temperatures, so being able to understand the interactions and movement of silicon nitride can provide useful information to those who seek its potential. The goal of these molecular dynamic simulations is to acquire a mean square displacement and relate it to a diffusion coefficient that can then be used to find activation energies for specific temperature ranges. Over the summer, I've been working with these models of silicon nitride and silicon carbide. Each model is a cubic box, with each side being roughly about 50 angstroms, or approximately 5 nanometers. There are two types of layers in the first three models, one which is made up of amorphous silicon nitride, and one which is made up of silicon carbide in an ordered bulk. As you can see, there are three different thicknesses for each silicon nitride layer, one with a thickness of 7 angstroms, one with 15, and one with 24. The last model on the right has no silicon carbide bulk layer and is entirely made up of amorphous silicon nitride, essentially making it an infinitely thick silicon nitride bulk model. Since I am currently focused on the two-dimensional diffusion of nitrogen, I'm only focused on the amorphous silicon nitride layer, so the silicon carbide layer is fixed in place for these simulations, making it so that no atoms from the silicon nitride layer can diffuse through it. Earlier this year, we ran simulations in which all atoms present were able to move, but at high temperatures of around 4000 Kelvin onward, the atoms essentially melt together, in which the silicon nitride layer and the silicon carbide layer are basically indistinguishable. In order to focus on the diffusion of nitrogen, we have fixed the silicon carbide layer in place so that none of the atoms are able to move, also making it so that the silicon nitride layer remains in the environment that it begins with. The MD, or molecular dynamic simulations, that I run are typically between the range of 2000 to 5000 Kelvin, with temperature increments of 200 Kelvin. The heating between each temperature lasts for 1 nanosecond, while each temperature increment is held for 5 nanoseconds. Now, these simulations do take some time to complete. A simulation in which each temperature increment is held for half a nanosecond will take anywhere from 2 to 4 hours, whereas simulations like these, in which they are held for 5 nanoseconds, will take anywhere from 36 to even 48 hours to complete. These times will vary between models, but after the simulations are complete, I am then able to look back at the data for the mean square displacement, or how much the nitrogen atoms have moved from their original positions over time. Since I am focusing on two-dimensional diffusion, I'm only looking at the x and y components of nitrogen's diffusion. As seen in the upper graph, which correlates to the 4000 Kelvin region, the x and y components when the x and y components are added together, they produce a rather linear slope, since both have relatively similar mean square displacement values. This can be seen in the green and the blue lines, which when added together produce the pink line, which correlates to two-dimensional diffusion. This differs from the red line, which correlates to the total diffusion, in the sense that there is no z component, or in this case, the black line. This is done because the black line, or the z component, creates a rather slight curve when taking into the total mean square displacement. And this is because the z component begins to level out as reaching a certain limit, which can be seen in the following graph, which correlates to 5000 Kelvin, in which the black curve begins to level out at around 100 angstroms squared, or 1 nanometer. Because of this trend, throughout all of the simulations, the z component is removed and I end up with the pink curve that relates only to two-dimensional diffusion. Once I have all the mean square displacement values for each temperature range as a function of time, I can then apply a linear fit to each line in order to extract the slope, which correlates to a diffusion coefficient. This can be seen in the bottom graph, in which each of the lines correspond to a different temperature between 2000 to 5000 Kelvin. If I apply a linear fit to each of these lines, I've essentially extracted the slope, or the diffusion coefficient, correlating to each of these temperature ranges. And once I have compiled a list of each of these diffusion coefficients, I can then use the data to create Arrhenius graphs. After gathering each diffusion coefficient, I can then make an Arrhenius graph, or rather an Arrhenius plot, in which the natural log of the diffusion coefficients are plotted against their respective inverse temperatures, which, when applied with an Arrhenius fit, will produce activation energies for linear segments in the curve. At lower temperatures, the diffusion coefficients don't become significant enough until after the kink in the upper 2000 Kelvin region. Because of this, I usually focus on the upper temperature regions in which more linear patterns can be seen, and this is most likely due to a phase change between a more solid phase into a more liquid phase in the silicon nitride layer. And as it can be seen in the 24 angstrom thick layer model, an activation energy of 337 kilojoules per mole is received for the range between 4,400 Kelvin and 5,000 Kelvin, which can be seen in the graph on the right. So, after applying the same process for creating the Arrhenius graphs to each individual model, we can see a general trend that as the silicon nitride layer increases, the activation energy decreases. For the 7 angstrom model, we receive a value of 834 kilojoules per mole for the 4,400 to 5,000 Kelvin region, which differs very significantly from the 15 angstrom and 24 angstrom models, which produce values of 353 kilojoules per mole and 337 kilojoules per mole respectively. And if we take a look at the infinitely thick silicon nitride layer model, we can see that for the same temperature range, we receive a value of 278 kilojoules per mole. One possible explanation to this trend could be that the impact of the silicon carbide interface in the thinner model being so close together is what produces the higher activation energies. So in order to disprove this or see if this trend actually continues, I am running simulations on smaller or thinner silicon nitride layers in which we have layers thinner than 7 angstroms and thicknesses between 7 and 15 angstroms to see if there is at some point that the activation energy suddenly spikes down. And in order to keep with, or be consistent rather, I'm also running new simulations on these individual models in order to see if I receive similar values. I would like to thank the PIRE program for giving me the opportunity to be performing this research over the summer, and to Sailesh for all the support and help that he's provided. Thank you all for your time, and I hope to be able to continue my research.